By now you're aware that our subject is weather. Weather related to forest fires. My name is Louis Allen. Weather is my business, and my job is to get across to you the importance and the role that weather plays in the start and spread of forest fires. Now, more specifically, there are several aspects of weather that must be considered. These are wind, lightning, humidity, and fuel moisture. Now, while all of these are important, wind presents the most persistent problem because it can change speed suddenly, it can change direction, it can become quite gusty without notice, as well as dry out timber, and in general be quite erratic in its behavior. Obviously, a strong wind increases the rate of burning. It can also increase the chance of spot fires, and wind usually determines the direction of fire spread. Wind is created by a variety of differing conditions. In order to help understand these better, we give them names such as gradient wind, gravity wind, and local wind. Now, at a fire, any one of these may be present, but usually they occur in combination. The first is a gradient wind. A gradient wind is named because of the gradient that exists between a high and a low pressure system. A high is a large invisible mountain of air in the atmosphere, whereas a low pressure system is like a sinkhole. Around the high pressure system, the wind flows in a clockwise manner. Around low pressure systems, they flow in a counterclockwise manner. When these highs and lows are well developed, the gradient winds are just that much stronger. The next wind that we have in mind is this. A gravity wind is sometimes called a fall wind or a foehn wind. The gravity wind. A gravity wind is so named because it is created by gravity, namely the heavier air spilling over high elevations and racing downhill. This also can occur when we have a high-pressure system located in a position like this. The flow of air around the high-pressure system causes some of that air to spill over the higher elevations, and this wind races downhill at a phenomenal speed. In so doing, it will dry out the timberland, the temperature increases, and the winds may run anywhere, possibly 50 up to 70 miles per hour, depending upon the stricture or the pass through which the winds are taking place. These are called gravity winds. Now, in Oregon, the gravity wind is referred to as an east wind. In Central California, a gravity wind is referred to as a mono. In Southern California, the gravity wind is the famous Santa Ana. Many of the large, damaging, and costly fires in Oregon, Washington, and California have been caused by gravity or foehn wind. Here is a typical Santa Ana wind affecting the Sierra fire on the Angeles forest. This is an east wind with surface speeds up to 35 miles per hour. With the accumulative dryness which existed, extreme rate of fire spread resulted. The fire was pushed by the wind with little effect from topography, and many spot fires were started ahead of the main fire. Now, the third wind that we have in mind is this. Local wind is so called because of the effects of local conditions and terrain in creating these winds. Now, there are many ways that this is done, and I have here an illustration of sort of an oversimplification, as it were, but for the sake of clarity, we'll use it. For example, during the daylight hours, when the sun is quite bright and the sun is shining sharply on the land masses as contrasted to a water mass, well, the land masses become quite warm, and the air over these land masses begins to rise slowly. I think we've all experienced this, particularly in the summertime. This air just keeps going up as it heats. The end result is that we've created a small pocket in here, and some air must move in to take its place. So the cooler, more dense air that is available, in this case over the water, begins to move in and take the place of the air that has risen. But in so doing, this air also becomes heated, and it too begins to rise, and finally we get a circulation around, and this is our convective cell that takes place in a very small localized area, so that we have this convective circulation as a result of the heating of the land mass, as well as the air over the water being a little bit cooler. Now, the reverse of this takes place at night. In this case, the water is warmer than the land mass. The ground has cooled considerably, and this air over the land is a little more dense, whereas the air over the water is less dense or warmer. So the air over the water, it begins to rise like this, begins to rise little by little, and then the downslope motion, or the downdraft off of the cooler land, moves in to take the place of the air that has departed and moved upward. As a result of this cooler air moving over the warmer water, it too then becomes heated, and it continues to rise to the point that we begin to get, again, our convective circulation taking place. This is just the reverse at night, as we see, from that which has taken place in the daytime. Now, similar conditions also take place in forested countries, wherein you get this differential effects of heating and cooling. Firefighters call this convective wind, downslope or downdraft. Downslope wind usually does not develop stronger than 3 to 5 miles per hour. Upslope wind during the afternoon often reaches speeds of 5 to 10 miles per hour. This is one reason a fire spreads faster uphill. The change of the flow of air from upslope to downslope is usually quite gradual, and during the time of this change, the air may be calm, say, for about an hour or more. Generally, the south slopes warm more during the daytime and cool more during the nighttime, thus producing stronger updrafts during the day and stronger downdrafts during the night. The general pattern, then, is upslope winds during the day, downslope winds during the night. But there are important exceptions, and the local fire people will know what these exceptions are, and they should be consulted. The important point to remember is that different surfaces absorb different amounts of heat, and the flow of air runs from the cooler to the warmer surfaces. We've now studied the different types of winds. There's the gradient wind, the gravity wind, and the local winds. Now, to make a difficult problem even more difficult, we must consider the effects of topography, as well as the type of ground cover. In flat country, wind is not greatly influenced by terrain, but wind speed and direction may be conditioned by the cover type, which may cause unequal heating and cooling. Obstructions may interfere with normal wind flow. Here, the wind follows the normal convective pattern. The shape and contour has much to do with wind direction and speed. Rough mountainous country, particularly ridges and mountains, are barriers to the horizontal movement of air. But passes and gorges funnel the wind through and increase its speed. It is similar to the increased speed of water flowing through a shallow or narrow place. Friction between the flowing of winds and rough terrain will create eddies. Sometimes these eddies are large and sometimes they're rather small. For example, suppose we have a flow of air at altitude like this. The flow also would be in the same direction along the terrain. But as we come to a high spot in the terrain, this convergence area will cause the wind to flow more swiftly and pick up its speed rather sharply like this. On the lee side of the mountain, atmospheric pressure will drop a little bit, causing the airflow to begin to develop into a large eddy. The stronger the wind flow, the larger the eddy takes place, actually blowing uphill in a direction contrary to the way it was originally blowing. If, for example, there was a fire on the windward side of this ridge area, the burning embers could be caught in this eddy and brought down on the leeward side of the mountain, and the threat of spot fires in this vicinity would be greatly increased. Whirlwinds are another form of erratic wind behavior. Air flowing over a ridgetop will start revolving. But aside from topography, fire creates a convective flow of air and contributes to whirlwind activity. Whirlwinds are common where heat favors the development of strong rising columns of smoke. Whirlwinds intensify burning and lift burning embers aloft, increasing the threat of spot fires. To summarize, topography affects winds, often causing to change direction or increase speed as it funnels down through valleys and canyons, causing it also to form eddies as it crosses saddles, and contributes generally to whirlwind activity. All of these wind variations are significant in fire suppression. Now, another problem has to do with ground cover. Now, bare slopes heat rapidly and cool faster than do forested slopes. Consequently, winds will be faster along bare slopes than they will along forested slopes because of the difference in temperature between these two land surfaces. Timbered slopes tend to reduce wind speed. Two other important weather factors that influence wind direction and speed are fronts and cumulus cloud formation, particularly thunderheads. During summer months, cold fronts are often accompanied by thunderheads, which produce strong, violent winds, even though they are of brief duration. Cold fronts generally move toward the east or southeast. As the front approaches, sudden, marked shifts in wind direction occur. Here we have a diagram of a frontal pattern which on the surface of the Earth would be range around 200 to 400 miles. We are principally interested in wind conditions in this pattern. The warm air, the flow is from the southwest. In this cool air, the flow is generally from the southeast. And in the cold air, the flow is generally from the northwest. The cold air pushing down the cold front in this direction, you can see that with the southwest wind, as the front passes, the wind would shift and become out of the northwest. In this band through here, we would have some cumulus cloud development, and gusty winds would take place along with a sharp, sudden change in wind direction. Now we have a diagram of this in profile. As this cold front, which we saw a moment ago, advances to our right, it releases the instability in this warmer air as it forces this warm air to rise. This instability creates large, severe thunderheads with strong, gusty winds at the surface. As a result, as the cold front moves through an area of a going fire, you can see how the wind shift, plus the strong, gusty winds taking place, would create an extreme hazard in the firefighting problem. At first, the flow of air out of the southwest causes fire spread to take place toward the northeast. As the cold front begins moving through, the winds shift, coming out of the west with the fire spread taking place toward the east. When the cold front is finally passed, the winds are now out of the northwest and the fire spread is now taking place toward the southeast. Now, gustiness is a real troublemaker and becomes more serious if the wind is strong and the wind direction is variable. Close liaison with the U.S. Weather Bureau fire weather forecaster will keep the forester informed on location, strength, and expected motion of cold fronts.
At 1400 hours. Expect strong, gusty winds from 1345 to 1530, shifting at 1400 from south to west.
It's going to be real hot.
Any great variation in wind speed, even if direction remains the same, will influence strategy in fire suppression. To recap, a cold front will change the direction of the wind from southwest to west to northwest. In addition, the passage of a cold front will create gusty winds. Now, as previously mentioned, thunderheads are another source of strong gusty winds. Often the sign of the developing thunderstorm activity is the appearance of altocumulus castellatus clouds. If they appear in the morning or late evening, you can expect thunderstorm activity later. Visual clues for possible gusty wind is the appearance of cumulus clouds. Any cloud with cauliflower appearance indicates upward motion of the air. The taller the cloud, the greater the upward motion of air. A cumulus cloud develops into a thunderhead when air currents reach a height, say, of about 25,000 feet. Now, these air currents are warmer than the surrounding air. But now the air current has reached a critical height where precipitation begins. The falling rain or hail indicates a strong downdraft below the cloud. This downdraft strikes the ground and spreads out, producing strong winds, sometimes as much as 70 miles per hour. The weather-wise forester should be alert to the extreme danger of sudden change in wind direction and wind speed. These often occur under the leading edge of an approaching thunderhead. Remember, surface speeds may increase from 5 to 70 miles per hour in a matter of a few seconds. This affects the holding of prepared lines, of burning out, and also the positioning of men for safety, as well as many other important facets of the fire job. Now, another facet of weather that is important, plays an integral role in the thunderhead, is lightning. Well, strictly speaking, lightning exerts very little influence of itself on a fire. However, it does start many a forest fire. Development of lightning requires cloud temperatures below freezing. Tall clouds which carry moisture up to the freezing level are signs of impending lightning storms. When the cloud top turns into ice crystals with a hazy, indefinite outline, the cloud has now become a thunderhead, and lightning may very soon follow. Precipitation is generally present before we have lightning, but yet we sometimes refer to dry thunderstorms. In this type of thunderstorm, the moisture is relatively high above the ground, or precipitation evaporates before it reaches the earth. However, it is quite common for lightning to reach the ground from these high thunderheads, and so we have dry thunderstorms or lightning storms without precipitation reaching the earth. There are two other closely related factors that influence fire behavior. These are humidity and fuel moisture. Now, while there are many ways of measuring humidity, what we are interested in is relative humidity because it's directly related to fuel moisture. Here, let me show you. In this diagram, this is midnight, noon, and midnight the following evening. This curve represents temperature, so that in the early morning hours we have a minimum temperature. When the sun begins to rise, the temperature begins to rise, until we reach a maximum temperature in the late afternoon. After the sun sets, of course, temperature drops off. Now, the behavior of relative humidity is just inverse, namely that in the early morning hours, our relative humidity is at its maximum, and it will decrease as the temperature increases. So the relative humidity decreases to a minimum in the late afternoon hours at the time of maximum temperature. This is the time, then, when there is a minimum fine fuel moisture. Fuel moisture is directly influenced by relative humidity. The ease with which forest fuels can be ignited, intensity of burning, and rate of fire spread all increase as fuels become drier. But during the night, the air cools, humidity increases, and fuel moisture tends to rise. However, in mountainous country, fire often does not stop spreading at night if it is burning on the mid-portion of slopes. Such areas, even on calm, clear nights, have less humidity recovery, and this is why. This represents one slope, like this, and a second slope, creating a valley. Now, we have learned previously that during the day, the thermal heating will create upslope motion of air, whereas thermal cooling at night creates downslope motion of air. However, in this instance, we have the valley pocket, and this cooler, more moist air finally settles in the valley pocket, while along the mid-slopes, the flow of air, as gentle as it may be, will continue to be downslope motion. It is for this reason that the middle third of these slopes is referred to as a thermal belt. We can expect active fire on this middle third. We've talked about wind and the causes which affect its direction and speed. We've touched on lightning, wherein precipitation reaches the ground, and dry thunderstorms, wherein precipitation does not reach the ground. We've seen the importance of humidity and fuel moisture, how they are influenced by temperature, and how they directly affect rate of burning and fire spread. Now, all of these weather elements played a major role in the Sleeping Child fire on the Bitterroot National Forest. We are now going to touch on some of these features, especially wherein the weather dominated the fire's behavior. The circumstances preceding the fire were extreme accumulative dryness and the large volume of down, bug-killed, lodgepole pine timber which predominated the area. The lack of precipitation left these fuels in extreme critical condition. The weather forecast for August 4th, the day the fire started, called for thunderstorms and gusty wind in the thunderstorm area. The lookout reported thunderstorm buildup approaching from the west. At 1600 hours, the thunderstorm flashed lightning over the Sleeping Child drainage, but no precipitation fell. Minutes later, a fire was reported to the district dispatcher. The size of the fire, 3.5 acres. The spread of fire was caused by strong downdrafts from thunderheads. Plan of action was to line around spots and burn them out. By midnight, all spots were contained according to plan. But that night, another thunderstorm with strong erratic winds hit the fire area, causing more spot fires. In the late morning, a spot was discovered 1/2 mile south of the fire line. It spread quickly. At noon, a special weather forecast reported a cold front moving in and to expect severe thunderstorms with extreme gusty winds up to 70 miles per hour. Before the cold front hit, most of the fire problems were to the north of the fire's edge. As the cold front moved through, the direction of the fire shifted from north to a southerly course, increasing the chances of spots along the southern sector. All line was lost, and the fire had consumed 10,000 acres in the past 24 hours. On August 10th, the fire weather forecast called for northerly winds this morning, which will push the fire southeastward into heavy fuels. Gradient winds are pushing the convective column to the southeast. Spot fires started 1/4 mile in advance of the fire front. At final control, 28,000 acres were burned. Cost almost $2 million. We have seen how weather affects fires. The base of any successful firefighting job is founded upon weather information. Fire weather mobile units are dispatched to fires where fighting is difficult, and these mobile units are operated by Weather Bureau fire forecasters. Frequent field observations in the vicinity of the fire perimeter is essential to accurate local forecasting. The Weather Bureau and its fire weather meteorologists provide information which the fire behavior officer uses in developing the fire behavior forecast. Your ability to control or suppress fires and to achieve economy in the use of supplies and manpower will depend largely upon your application of weather information to the problems of fire control and to close cooperation between you and the weatherman. In the final analysis, however, you must add your own knowledge and understanding of fire behavior. As fire control men, the weather indeed is a very important part of your business.